The name of this video is Magnetic Field B. So for the first time, we depart from only the description of the electrostatic field, which we have done up until now. And in fact, we are going to generalize it in this video to the concept of electric field, not anymore electrostatic field. And we are also going to introduce a new fundamental field, which is the magnetic field indicated as B. It has many names, magnetic induction, but it's basically the magnetic field. So supposed to have a set of source charges in a region capital omega in space. So in this region, capital omega space, we can have a discrete set of charges, for example, Q1, Q2, etc., all the way to, let's say, Q capital N. We can also have a set of continuous charge distributions, for example, with volumetric densities rho, rho prime, etc. It can happen that these source charges, so these are my source charges, so it can happen that these charges are either at rest in an inertial reference frame, IRF, or they move in the same inertial reference frame, IRF. These are the two possible options we have. They can either be at rest or they move. Actually, in the previous video, where I introduced the concept of dynamic charge, we were considering all the source charges to be at rest and only the test charge to move. Now we want to investigate all possible scenarios, which is 4 of them, which I'm about to summarize in a table here. So where the source charges can either be at rest or move in an inertial reference frame, and the test charge also can be at rest or move in the same inertial reference frame. So in fact, let us consider a charge here, let us call it Q naught, at the point capital P. This is my observation point, where I want to observe the overall force due to this set of charges, which in principle can be static or move, at rest or move. So I want to investigate the total force there. Okay, so obviously we know that if these charges were at rest, nothing was moving, clearly we should expect here to see only an electric force, okay, an electrostatic force in fact, and so only an electrostatic field E. In general, the situation is a little bit different. So let us summarize what's happening here with a table where we have the following entries. So we can have the source charges, we can have the test charge, and here we see the force F at point capital P. We measure the force F at point capital P. Okay, so the first scenario is when, let's call an average velocity of all these charges, just for simplicity. Each of them, of course, will have a velocity, just to refer to them. If they're not at rest, if they move, let's say that they move with the velocity v vector of the source charges, or Q, whereas if Q naught moves, let's say that it moves with a velocity v of P, okay? And this velocity can be function of position, r, and time. Similarly here, this can be function of position and time. Okay, so these are the velocities, which again, if they're 0, it means these particles are at rest. If not, they're moving. So what happens if the source charges, they are characterized by a velocity vq equal exactly 0. So they are all at rest. Okay, this just in brief means they are all at rest. And also, let's say the test charge Vp is at rest. So everything is at rest. Well, as I already said, then we go back to the electrostatic case, which we studied up until now. So in this case, we know that the force has to be an electric force, okay? And this is equal to the test charge Q naught, which is our charge here, point capital P, and multiply times the electrostatic field due to all these source charges, which is E a point R. And in this case, since everything is not moving, there is no time dependence. It's just the usual E at R which we encounter up until now. So this one is the electrostatic field. Okay, the electrostatic field, no time dependence whatsoever. Same as all we've done up until now. Now, suppose now instead that the source charges are still at rest, so they do not move, so VQ is equal to 0. But the test charge moves. Vp is different than 0. And this is all from empirical evidence, okay? So it's all experiments that people have done, and they found all what I'm saying, what I'm summarizing in this table. So from all this empirical evidence, people found experimentally that in this case, the force acting on Q naught is exactly the same as the one up here. So again, the source charges only create an electrostatic field. Where again, I stress the fact that these are static fields. Okay? Now, what happens if, in the next entry of the table, we consider the case where VQ is different than 0. So this is the first time where we hypothesize that actually the source charges are moving in space and time. But let's assume that the test charge is now not moving. In this case, from the experimental evidence, we find that the force looks very much like the one up here. So it's still given by Q naught, the test charge, times an electric field, E. But now this field is generated by a set of moving charges, and this field can depend on time. So since now this field is generated by moving charges, we don't call it the electrostatic field anymore, we call it the electric field. So electric is more general. The electric field means that this field can vary in time, it's a dynamic field. Okay, it's also called dynamic. A dynamic field. In 342, we are going to extensively study all these dynamic fields more in detail. Okay, so as it turns out, this field is not the same as this field here. So electrostatic and electric are actually different. That's why we also use different names and call them in a different way. Now, the last entry of this table, which is the most complete and most interesting perhaps of them all, is the most complex scenario where both the source charges move, as in here, and also the test charge moves. So everything now is dynamic, okay? So it's a complete dynamic scenario here. So what happens in this case? Well, from the experimental evidence, it so happens in this case that the force F acting on Q naught, it still happens to be proportional to Q naught. That's the same. But it's a little bit more complicated because it has two terms. The typical electric term, which is Q naught times E, but it's electric, not electrostatic, so it's a function of R, as well as T. But there is another term, plus the velocity V of what particles? The test particle, in this case Vp, cross vector product with a new quantity, B, which in general is also a function of R and T. And this quantity, we call it the magnetic field. So this is the first time we encounter a magnetic field. As it turns out, the reason why you can have a magnetic field is because these charges are moving. So in fact, in both these cases, there was a magnetic field, okay? So as soon as you have moving charges, you have a magnetic field, no matter what. Let me put it in parentheses here. This is happening for sure in both cases because the charges are moving. However, if the test particle is not moving, I cannot detect it. So it's there, but it basically as if it wasn't there. Whereas if this particle is moving, then actually I can detect it. If I measure this force, I see a difference when this particle moves. So in order to see a full effect of the magnetic field, I need to generate it, and in order to generate it, I need moving particles. Here B is equal to 0 in all these cases. So I need these moving particles, but I also need a moving test particle to detect it, okay? So this is called the Lorentz force. Okay? So as it turns out, again, all this discussion stems from purely empirical evidence, that is from experiments. From experiments, people were able to find Lorentz force, which has this form by means of measurements. You could, if you wanted to, prove this force by means of the least action principle. Landau does it, Feynman does it. It's very complicated, and I don't think it's worth, and it's good to do it pedagogically in this specific course. Okay, however, you could prove this from basic principles. Okay, it's very interesting by means of the least action principle, and which is something which perhaps you've seen in analytical mechanics, in classical mechanics. We can actually prove it from fundamental principles. But here I prefer to introduce it experimentally. Okay, so if you take a more advanced course on electrodynamics, one day you will understand how this can be proven from fundamental principles. But remember that it doesn't matter if it's a theorem, that is, you prove it from principle, or you take it as empirical evidence and you call it a principle. In the end, all these things that we do in physics stem from experimental evidence. Somebody has to do experiments to show that things are true. So I actually really like to introduce it from an experimental perspective, because that's the way people actually measure it. So, to summarize this video, for the first time we introduce the concept of a magnetic field B. The magnetic field B can only exist if the test particles move. Okay, and in fact, when they move, what they generate is something which is called a current. Okay, so a current could be a current of a single particle. So one of them, I isolate it, moves, it generates a current. Or all of them, they move, they also generate a current. For example, the typical current you're used to, which we'll study in a few videos from now, in conductors, is due to the moving electrons. So you can have an ensemble of electrons moving. Anyway, you need a current, which again can also be of a single particle. And in order to, so this generates an electric field, which is function of time, a dynamic electric field, which we don't call it electrostatic anymore, and also a magnetic field B. However, to detect this magnetic field on a test particle, you also need one that this particle moves in space and time. So in that case, you find the Lorentz force, which is summarized down here. That's it.